Hello everybody, and welcome to the beginning of page 5 in the workbook. We are looking at definition 1.0.5. This is the last of our list of definitions, and it talks about two special types of matrices that come up often in our course. Okay, so let's read this together. So first thing we're going to talk about is the m by n zero matrix. Our book's notation for this is going to be this big O. If you look carefully at it, it's italicized. And here's the actual definition. Okay, it tells us that the entry in the ith row and the jth column of the zero matrix is 0. Okay, now this is just a really fancy way of saying that every single entry in a zero matrix is going to be 0, okay, regardless of what the size is. Okay, and the second part of the definition is what's known as the identity matrix. Maybe some of you have heard this term before. An identity matrix is always a square matrix. Okay, same number of rows and columns. Our notation for it is going to be to use the letter I. And here's the formal definition. It tells us that the entry in the ith row and the jth column is going to be 1 if the entry is in the same row as it is in the column and 0 everywhere else. This is just a fancy way of saying that an identity matrix has 1 on the so-called main diagonal and 0 everywhere else. Okay, we're going to write down a couple of specific examples of that in just a second here. Okay, so just to illustrate the two definitions here, let's write down some examples first of zero matrices. Okay, so again, a zero matrix is just a matrix that has zeros as all of its entries. So there would be the 2 by 2 zero matrix, or that's also a zero matrix. That's also a zero matrix. So basically, any matrix that just has all zeros in it is going to be called a zero matrix. And there's a basic property. Okay, what's special about a zero matrix, or one thing that's special, is that if you take it and multiply by another matrix, you always get 0. Okay, provided, of course, that the matrices are the right size to take those products. So let's say it this way, provided that the products are defined. Okay, well, what about some examples then of identity matrices? Okay, well, here would be the 2 by 2 identity matrix, so it's going to have 1s on the main diagonal and 0s everywhere else. The 3 by 3 identity matrix would look like this. Okay, so 1's going down that main diagonal and 0 everywhere else, and so on. Okay, and anybody remember what's special about the identity matrix, why we give it that name? Okay, well, you might remember that the identity matrix kind of behaves like the number 1 if we're talking about real number arithmetic. In particular, if you take A and multiply it by the identity matrix, or if you do it in the other order, you just get the same matrix A back again, just like the number 1 works if we were talking about real numbers here. And again, provided that the matrices in these products that we're writing down are the right size. Okay, so provided the products are defined. Let's give one specific example just so that you can see that in action here. So if we were to take the 2 by 2 matrix 1, 2, negative 3, 4, and multiply it by the 2 by 2 identity matrix, what you would discover, I'll let you confirm this on your own, is that you would just get the same matrix 1, 2, negative 3, 4 back again. Okay, and if you multiplied in the other order, the same thing would happen. Okay, so the identity matrix times 1, 2, oh, whoops, I'm sorry, I wrote one of my entries wrong. Okay, that should have been a positive 4. Okay, like that. Okay, so that's the basic property that an identity matrix has.